I will do in these few sessions is I will go through the problems I have given you. You will solve them. We will go through them in detail. But I have mentioned this earlier. Just don't look at the problem solutions over here and say, I think I understand. And go back and that's enough preparation. I am not trying to prepare your exam, by me doing this problem. I am not telling you how this must be done. So you will have to go back and redo these problems all over again and make sure you have really understood and internalized them. Otherwise, you will spend a lot more time in the exam going through all the pitfalls that you probably will have the first time you do it. So you have to do it a few times and ensure that you have completely understood it. And I am trying to only help you in going through this process because it's quite likely that some of you haven't got the hang of some of these problems. And that's what I'm doing. But this is not a substitute for yourself doing these problems back in your room. Let's take the first one. And essentially we went through electronic spectroscopy and we said that there are under certain conditions you will get what is called a sequence band, and under certain conditions you will get a progression. Now what do you mean by a sequence band? Just delta V equal to 0. So you will see whatever potential curve here and the potential curve here, and V equal to 0, V equal to 1, with V equal to 0, V equal to 1. I call this double prime, single prime. As a notation that we normally use in spectroscopy, double prime for ground state, lower state, and single prime for the excited state. So if I go from 0 to 0, the transition, it's a 0-0 transition, and the delta V in that case is 0. So from 0 to 0. If I go from 0 to 1, then delta V of course is 1. While in vibrational spectroscopy, there is a selection rule that tells you that you can only observe delta V equals plus minus 1 transitions. We saw that in electronics transitions, there is no such selection rule. And we are essentially guided by the Frank-Horner principle to determine what levels the excited states are accessible starting from a given level in the ground state. For pure vibrational spectroscopy, V equals 1 can only be accessed by V equal to 0. V equals 2 can only be accessed by V equal to 1. Because you have a delta V equals plus minus 1 selection rule. But V equal to 1, can I see from V equal to 0? I don't know. Because that is essentially told to me by how these two potential curves are located one above the other and what their shape is. So the Frank-Horner principle essentially decides for me what levels in the excited states are accessible starting from a given level in the ground state. Now in this connection we said that the two states are very similar looking, meaning that the shape and potential. And when the shapes can be very different because the shapes are guided by how the electrons are located within that molecule, how they are distributed within that molecule. You can have states like this, you can have states like this, you can have states that are very close, meaning they are very bound states. So we can have that. But then we also said that if I remove, for example, an electron from an antibonding orbital, and put it into another antibonding orbital, or go from bonding to another bonding, the shapes don't change by all order, because I still maintain my bond order. So the states don't change, and the individual distance does not change. Then there are two potential curves that basically line one on top of the other. And therefore, if I start from V equal to 0 and go to this V equal to 0, what is that intensity guided by? It is guided by the Frank-Horner factor. And what is the Frank-Horner factor given by? Psi prime, psi double prime, beta, and of course, the square of this. So if this state and this state are bang on above each other, then what happens? This wave function and this wave function will actually overlap beautifully. And the overlap will almost be equal to 1. If that is equal to 1, then I know that the entire transition is basically limited from here to here, because we also there's a called a closure rule that if I sum all the Frank-Horner factors starting from here to every other level, that should be equal to 1. But by going from 0 to 0, if I already have hit 1, I don't have any transition left for other transitions to be seen. And therefore what I will see is just 0 to 0 and nothing else. If I go from 1, I will see 1 to 1 and nothing else. Now this is the situation. The two potential curves are very similar in shape and are lined just one above the other. And then in that case we say I'm actually looking at a sequence transition which is 0, 0, 1, 1, 2, 2 and so on. But what happens in the state above is shifted. You see I've slightly shifted it up. then what happens? This and this really don't have complete overlap. They only have partial overlap. And therefore, if I work this out on the 0-0 transition, what would that overlap integral be? The square of that, maybe 0.2. What does that mean? There is still 0.8 worth of transition somewhere else. And what would that be? 0, 0, 0, 1, 0, 2, and so on. In other words, the moment the curve is shifted that way, what I'm essentially telling you is, the molecule make the transition from this level, and it could make it from any one of these points. Meaning, either it is vibrating back and forth, it could jump out from here, anywhere. So if we jump out from here, maybe you will reach this. If I jump out from here, I will reach this. If we jump out from anywhere in between, I will reach any of these, from the Frank statement of the Frank quantum fields. So what does that mean? It simply means the potential curve is shifted just a little. I can actually see transition from 0 to 0, all the way from 0 to 8, 10, 12, so on. What I exactly see depends on the shape of the potential and how much it is shifted by. Well, you can actually make a quantitative estimation of that by doing a Frank quantum calculation, but that's not what I'm asking you. The first question actually says, in this ground electronic state, X is the vibration frequency of 212 wave numbers. So this is the X state for ID has 212 as omega E and an RE of 2.66 angstroms, meaning that this is 2.66. An excited electronic state B has the following properties. So let's say this is B. And how much is B? 3.03. Let's say this is the B state. And what is the R going to be in this case? 3.03. And what's the vibration frequency? 125 wave numbers. Why is this information given to you? If the vibration frequency is very different between these two, what is it really telling you? And the shape of the potential is very different. That's what it is really telling you. If the vibration frequencies are the same, it simply means the potentials are very similar looking. But the fact the vibration frequencies are very different tells me that the shape of the potential is very different. This is 212, this is 125. Which do you think will have a smaller dissociation in it? The 212 or 125? Smaller dissociation. The frequency is larger. The frequency is larger, what does that mean? The force constant is larger. The force constant is larger, then you expect the molecule to be more bound. So this is probably going to have a larger dissociation energy than this, so which means that while this might go like this would flare out much more rapidly, meaning the shape of the potential is going to be different. That's what I'm trying to explain to you. So the vibration frequencies are different. It's sort of telling you in some way that the shape of the potential is a bit different. That's the reason why that number was given to you. What about the RE? One has 2.66, the other one has 3.03. What is it really telling you? The RE has got longer, the force constant has got smaller. So what sort of a transition would this have been? Maybe I'm going from a sigma bonding orbital to an anti-bonding orbital when I do this. And that is the reason why the frequency has become smaller, the bond length has become longer. So I've actually gone from a bonding orbital to maybe an anti-bonding orbital. In another electronic state, little a, it has the following properties. The vibration frequency is 205. What does that mean? 205, this is 212. Very similar. Not very different. At least it's better than this. So what is that telling me? The shapes of the potential are probably very similar. And what more do I know? It has an RE of 2.75 as opposed to an RE of 2.66. So which means that this curve is probably going to be somewhere over here and having a shape that is very similar. And now the question is, transitions are observed between X to B and X to A. I can go from X to B, I can also go from X to A. Which of these two transitions is likely to show a long progression of vibrational bands? So all the discussion had earlier, we just have to apply it in this particular case. So which one would we expect a longer progression? We saw that longer progression is always observed if the two states are not similar in shape and they're shifted relative to each other. So in this case, B is shifted more relative to X than little a is. Therefore, in the case of A, you probably will see a sequence transition. But in the case of the X to B, you will probably see a vibration progression, and which is exactly what happens in the case of ID. The numbers given to you here are all real numbers. That's in fact the information that I pulled out for the ID model. So you look at ID in X to A, you've got just one or two bands, and that's it. But look at X to B, you'll have a whole series of bands. The reason why you have a whole series of bands is because the upper state is shifted out, and the transitions can actually span a whole region of vibration levels. In fact, the spectroscopists would like to use the term that the Frank-Condon region, which means going from here to here, all these levels. That's the reason spanned by this distance. That's what we call the Frank-Condon region is much greater than the Frank-Condon region for the little a transition. Therefore, the answer to that would be, you sort of explain this. See, it's shifted, because it is shifted, you span or you observe a longer progression, and therefore X to B would show you the longer progression than X to little a. And that's basically, in a way, we're trying to see how to apply the Frank-Condon principle to a problem of this sort. Okay, any questions? So in this, as I go along, if you have any questions that's not clear, you have to ask me right there, so that I can sort it out for you. We therefore take it that this is clear, but where this were to be asked, of course, I won't ask you this, but then in some other form, if you ask me, you will have to give me an answer that the logic has to be well explained. You have to go through the whole process of telling me why you chose a given answer. Just don't tell me that X to B will give me a longer progression than X to A. I won't give you any marks for that, because that's guessing. If you give me X to A has a longer progression than X to B, which is wrong, but you have some thought process in your mind that goes on, however wrong it may be, I might still give you half a mark or 1 mark, because you are trying to dig up an answer for it, try to dig up a reasoning for it, and that's what I'm looking for. But if you just tell me X to B is longer progression, even though the answer is 100% right, you get nothing for it, because I could have simply assumed that you just guessed it. And every question you'll probably see somewhere that I would write, briefly explain your answer. I need that. So you've got to give me an explanation. So even if you're wrong, you get something out of it. If you don't give me an explanation, even if you're right, you get nothing out of it. Okay. What's the next question? If the rotation structure, the vibrational bands were to be analyzed, in the above transitions, what would we observe? See, we saw this red degraded edges and the violet degraded edges, right? We saw that the band head, we have a progression. And what happens eventually at some point, if you have the rotational lines, or the progression, rotational lines, you see them, then for the rigid rotor, what's the situation? Equally spaced, no problem at all. But then we know there is no such thing as a rigid rotor. Every rotor will suffer from centrifugal distortion. If it suffers from centrifugal distortion, you see that the bands tend to close out. That's one problem. What's the other reason for which the band would close out? If the B value in the lower state and the P value in the upper state is not the same, we saw that equation where you have a J square dependent B prime minus B double prime J square. Then you will find the J square term will actually have an effect on the whole process, and therefore you will see that the rotational lines actually don't go equally spaced. Even if there was no centrifugal distortion, the fact that B0 and B1 are different, based on the equation which you wrote earlier, the rotational lines tend to get closer and closer and closer, and at some point they will all jumble up and then they start coming back. So you have this turnaround of the rotational lines, and then we say it's a band head. Now the question is the B branch going to turn around or the R branch going to turn around? If the R branch turns around, then I have a red degraded. Okay. If the P branch turns around, then I have a violet degraded. But then we also saw, when does the R branch turn around and when does the P branch turn around? If the upper state is out this way, relative to the lower state, then what happens to B prime? B prime depends on the R value. So R is greater, then B prime has got to be smaller. So if B prime is less than B double prime, go back and look at those equations, you will find the R branch is the one that will turn around. But if this curve is shifted to this side, what happens? Then B prime is actually greater than B double prime, and then you will see that it's the B branch that will turn around. So by actually looking at the band head and noting whether it is a red degraded band head or a violet degraded band head, actually gives you information on whether the upper state is shifted outwards or whether it is shifted inwards. So that's basically the question I'm trying to ask over here. What could you observe? Red degraded bandits or violet degraded bandits? Why? In which of those two transitions would the turning around or the rotational occur at lower gain? First, in both cases, what happens to the upper value, upper state B value, or the upper state R value? This is 2.66, this is 3.03 and 2.75. So in both cases, the upper state potential is towards larger R. If it is towards larger R, then what would you see? Red or violet? Red, no question at all. So both values will give me a larger value of this thing. Now tell me, which of these will turn around at a smaller gate and which of these will turn around after a long distribution gate? Now think back. If both values were the same, will I have a turning around or not? No. If both values are the same, there is no turning around. So if the two values are very close to each other, there is no turning around. If they just differ by a very small amount, then what will happen? They will turn around, but at very, very large gates. But as the value gets bigger and bigger in difference, then what will happen? They will turn around rather quickly. So even if you didn't know the answer, if you didn't know how to analyze this result, start from first principles. When B naught and B prime are same, which is what we did as the first approximation, as the first problem we did. And what did we say? If the two are the same,